Binomial distribution and hypothesis testing. So in this video we're going to have a look at 4 questions that are taken from practice exam papers for the MEI specification. We're going to look at questions that involve the binomial distribution and hypothesis testing. So in the first example we have a screenshot which shows the probability distribution for a discrete random variable x, where x is binomially distributed with n equal to 20 and p equal to 0.9. On the side we have the probability distribution written out as a table, so each possible value of x is represented by k, where k could take the values from 0 up to 20, integer values from 0 up to 20. And then next to that we have for each value the probability of that value occurring. So px equals k. Now, first of all, we need to describe the shape of the distribution. I always like to draw in the shape like that. You can see that the bulk of the data is on the right-hand side and the tail points towards the negative direction. So this is what we would describe as negative skew. It's always the direction of the tail that tells you about the skew. Now, part 2, explain why the values of px equals k for k equals 0 to 10 inclusive are recorded as 0 in the table. So in the table, you can see that for all the values of k from 0 to 10 inclusive, the probabilities are listed as 0. And this is because the probabilities are so small that they have been rounded down to 0. It looks like all of these probabilities here have been given to 4 decimal places, so the values for probabilities have been rounded to 4 dp, and the values of probabilities for k values between 0 and 10 must round to 0 to 4 decimal places. And for the last part of the question, state which of the values from 0 to 20 is the most likely value of x. Well, look at the graph and see which has the tallest bar, 18. So 18 is the most likely value, and the least likely value of x will be 0. That will have the smallest probabilities. As you can see, the probabilities start to tail off at this point and get smaller and smaller as the value of k gets less and less. So, second example, we have some important context at the beginning that we need to read through carefully. So between the islands of Tenerife and La Gomera, there is a resident population of pilot whales. Studies in the past showed that 20% of the adult population were male. Due to a change in environmental conditions, it is thought that the proportion of males has decreased. In order to investigate this, scientists caught and released a random sample of 43 different adult pilot whales. Exactly 3 of these were found to be male. So all of the information that I've underlined here is going to be crucial in answering this question. So there'll always be key pieces of information that we need to make sure we're aware of in a question. So carry out a hypothesis test at the 5% level to investigate whether there is evidence that the proportion of males has decreased. So we need to make sure we understand what our distribution actually is in this question. So the first thing I would make sure I did was to write down what x is. So x is the number of adult male pilot whales. And we think that x in the past has had a binomial distribution, and we're working with an n value of 43, and in the past the p value 20%. Remember, probability and percentage and proportion, the 3 p's essentially mean the same thing when we're dealing with statistics, so p equals 0.2. So that's the background information. Now let's set up the hypotheses. The null hypothesis H0 will be p equals 0.2, and our alternative hypothesis H1, well, we're testing to see if there's any evidence that the proportion of males has decreased. So p is less than 0.2. You can always get the wording for your null hypothesis from the question, so read it through really carefully to see exactly what it is. Now we need to define p. So I'm going to say P is the probability that a pilot whale selected from the population is an adult male. We could also have said that P is the proportion of adult male pilot whales as well. That would have been an appropriate way of phrasing it. We need to make sure that it's clear that P represents a proportion or a probability. So what do we now need to do? Well, we have a test statistic, which is that exactly 3 of our sample of adult pilot whales is male. So we need to work out the probability based on this. So remember, we're looking at a lower tail test here. P is less than 0.2. So we want to work out the probability that X is less than or equal to 3. So essentially our scenario, which is that 3 of the whales were male, but also the worst case scenario, the more extreme scenarios than that we have fewer than 3 adult male pilot whales, because remember, we're testing for evidence of a decrease. So we never do an equals to calculation. We would never work out Px equals 3. We work out the probability that X is less than or equal to 3. Now, to do this calculation, I'm going to immediately pick up the graphical calculator to do this, and I always work in stats mode for these calculations because it's much easier than doing them in run mode. So in statistics mode, we need to choose distribution, which is F5, and from there we want binomial, which is also F5, and then we want the binomial cumulative distribution, which is BCD, or accessed with F2. Now from there we need to make sure we've set up everything on the calculator correctly. So you'll see that the data needs to be set up as variable, and then we need to enter in the probability calculation values for upper and lower. So we're calculating the probability that X is less than or equal to 3, so the upper value needs to be set as 3, and of course the lowest possible value is 0. So effectively the probability that X is less than or equal to 3, we're working out the probability that X is in between 0 and 3 inclusive. Now the number of trials next needs to be set as 43, because that's the sample size that we're working with, and the p-value of course is 0.2, the p-value for the question. Now input all of this correctly into the calculator and we should find that we get a probability value at the end of this which is equal to 0.0177638. We're going to convert that to a percentage and round it, so I'm going to say that that is 1.8% to 2 significant figures. You could say 1.78% if you want to round to 3SF, but it's such a small value that 2SF I think will be fine. Now, we always then need to finish off by comparing to our significance level. So the significance level in this question is 5%. So we want to say that this value is less than 5%. It's less than the significance level. So what we're saying is there is a small probability of this scenario occurring, which means the result is actually significant. So the result is significant at the 5% level. There is sufficient evidence to reject H0. We should always frame our conclusion in terms of H0, never in terms of H1. And then our last comment is always in the context of the original question. So go back to the wording of the question. We were testing to see whether there was evidence that the proportion of males had decreased. So what we can say is we have evidence to suggest that the proportion of adult male pilot whales has decreased. Notice the non-assertive conclusion here. I haven't said we've proven, I haven't said we've shown, I've said we have some evidence to suggest that the proportion of adult male pilot whales has decreased. So always think through your conclusion, it should have 3 points to it. Think of 3 bullet points. So to start off with, we state whether the result is significant or not. We state whether we have sufficient evidence to reject H0 or not. And then we have a comment which is in context of the original question. So 3 points to the conclusion. Now, we're going to have a very quick look at an alternative method for doing the same question using critical regions. Now, I would not advocate using critical regions unless you're actually asked to do so, because it's more work. There's more work involved in solving a problem using critical regions. It's much, much quicker to do the probability calculation, which can be done in a few seconds on your calculator. However, you may be asked to solve a problem using critical regions, and to understand how to find the critical regions critical region for a hypothesis test is very important. So, if you remember the distribution that we were working with, X is a binomial distribution with an n value of 43 and a p value of 0.2. Now, the significance level is of course equal to 5%, and we were dealing with a one-tailed test, and it was the lower tail that we were dealing with. So how do we know that? Well, remember our H0 was p equals 0.2, and our H1 was p is less than 0.2. So the fact that it's a less than tells you it's a one-tailed test. Less than or greater than are one-tailed tests, and the fact that it's less than tells you it's specifically a lower tailed test, whereas greater than would indicate an upper tailed test. Now, let's think about the critical region. So I would say that a value, let's call it k, is critical if the probability that x is less than or equal to k is smaller than the significance level for the test, which is of course 5%. So any value k that satisfies this will end up being what we call a critical value, which will lead to a significant result. So what we can then do is use the calculator to identify critical values. Now, what I'm going to do is use the inverse binomial here to help me a little bit. So again, on the GCalc, I make sure that I'm in stats mode, and then I want to go to distribution again, which remember is F5, and binomial again, which is still F5, but this time I'm going to use the inverse binomial, or inv, which is F3. Now, the settings are similar to last time, and what I want to do is make sure that I have everything set up as it should be before I proceed. So let's have a look at what we're required to input here. So I need to make sure that data is set at variable. The area refers to the significance level, so that's 5% or 0.05 when converted to a probability. The number of trials is the value from the question, which is 43, and p is the probability from the question, which is 0.2. Now, where do I go from here? I then allow the calculator to run this, and it should then come up with something that says x inverse equals 4. Now, that's telling me that 4 is potentially going to be a critical value, but the calculator does the inverse binomial in a somewhat blunt way because it's a discrete distribution. So what I want to do is actually test whether this is indeed correct. So I'm going to go back into the normal binomial cumulative calculation, the same one we did last time, and I'm going to check whether this is actually correct. So I'm going to check the probability that x is less than or equal to 4, and I'm going to make sure that that actually falls within that critical region. So the probability that x is less than or equal to 4 is actually equal to 0.0505718, which interestingly is equal to 5.1%, which is greater than 5%. So actually, 4 is not a critical value. And it's really important to actually test this to check whether the inverse binomial has given you the correct values. The inverse binomial will give you an indication of the correct critical values, but it may not give you exact critical values or values that will end up with a significant result. You've always got to check them. So 4 is not a critical value, which means anything above 4 will also not be small enough to be a critical value. But if we check the probability that x is less than or equal to 3, well, we have actually worked out that probability already, but let's write it down again. That's 0.01776, etc., which we can say is 1.8%, which is less than 5%, so 3 is a critical value. So the critical region for this test is the set of values x, 0, 1, 2 and 3. These are the critical values. So if your hypothesis test results in, if your experiment results in any test statistic that is 0, 1, 2 or 3, you know you've got a significant result. Now, our sample of pilot whales said that there were 3 adult males in there, which suggests that that's a critical value, so we end up with a significant result. So if we end up with a test statistic that falls in the critical region, we have a significant result, sufficient evidence to reject H0, and evidence to suggest that something is going on. In this case, evidence to suggest a decrease in the proportion of adult males. So the conclusion can follow on in exactly the same way. Now, this is a more complex way of running a hypothesis test, but it is nonetheless a valid way of running a hypothesis test and one that you may be asked to actually carry out. So let's have a look at example 3. You may wish to actually read the problem yourself, have a go at the question, and then check your answers afterwards using the video to help you. So, let's read through the information in the question. The manufacturers of Miracle Root claim that as long as their instructions are followed, 80% of cuttings taken from Christmas trees will grow roots and develop into healthy new trees. A horticulturist suspects that this claim is optimistic. He takes 500 cuttings and, after carefully following the manufacturer's instructions, finds that 380 of them develop roots and developed into healthy young trees. Carry out a hypothesis test at the 1% level to determine whether there is any evidence to suggest that the manufacturer's claim is optimistic. So some key points highlighted and underlined here in the question. So as always, it's really important to identify what you are counting in this distribution, and also to understand why this is a binomial distribution as well. So I'm going to say that x is the number of cuttings that develop into new trees. Now, as soon as you see this, x is the number of, then you're counting the number of cuttings. Now, the cuttings have 2 options. They develop into new trees or they don't develop into new trees. That's a good indication of the binomial distribution. We also have a finite number of trials here because we only have 500 cuttings in the sample. So all of these are good indicators that we are dealing with the binomial distribution. So always define your random variable x that you're working with so you know what type of hypothesis test to run. Now let's set up the distribution of x. It's binomial, n is 500 and p is originally said to be 0.8, although the horticulturist disagrees with this or has a different opinion here. Now, let's set up our hypotheses next. So H0 is going to be the status quo, P equals 0.8. Remember, 80% of cuttings is the claim that will grow roots. H1, now let's try and translate the belief here for the alternative hypothesis. We're trying to find out whether there's evidence to suggest that the manufacturer's claim is optimistic. So the manufacturer thinks 80%, the horticulturist thinks that's optimistic, so the horticulturist thinks that the proportion of roots that develop into new trees, the proportion of cuttings that develop into new trees is less than 80% or a probability smaller than 0.8. We must define P, we absolutely must. So P is the probability, and you could frame this in terms of proportion as well. I've chosen to use the word probability. P is the probability that a cutting treated with miracle root selected from the population at random develops into a healthy new tree. So now that we have our hypotheses set up and P has been defined and we have our distribution ready to use, we need to do our probability calculation. So our test statistic is 380. We're given that information in the question here. So we need to work out a probability based on that. Look at the type of hypothesis you have for your alternative hypothesis. It's clearly a one-tailed test, and we're dealing with the lower tail here. So we need to work out the probability that x is less than or equal to 380. And again, I'm going to do this on the graphical calculator as simply as possible in statistics mode. So we want distribution, binomial, and binomial cumulative distribution, which is F2. So for the settings, the data is set at variable, the lower value is 0 again, the upper value is 380, the number of trials is 500, and the probability is 0.8. So this then gives me a probability value of 0.01600918, which I'm going to convert to a percentage and round two significant figures. That's 1.6%. Now, we're testing at the 1% significance level, so compare this to 1%, greater than 1%, so we can say that the result is not significant at the 1% level. And remember, the third comment is always in the context of the problem, and we were testing whether or not the manufacturer's claim was optimistic, so we can say something like, we do not have evidence to suggest that the manufacturer's claim was optimistic. So, what if we had wanted to solve this problem using critical regions rather than a p-value calculation? So remember that the distribution x is binomial and the n value is 500 and the probability value is 0.8. So if a result falls in the critical region, let's call it k. So if a value k is critical, then the probability that x is less than or equal to k must be smaller than the significance level of 1% or 0.01. Now, how do I know that it's less than or equal to k? Again, remember the format of the alternative hypothesis, which is p is less than 0.8. So we're looking at the lower tail here. So I'm then going to go to my calculator, and I'm going to use the inverse binomial again. So if you remember, that's distribution, binomial, and then the inverse binomial. And I'm going to see what happens when I set everything up. So this time, the area needs to be set as 0.01, which is our significance level. Our number of trials, n, is of course 500. And our probability value is 0.8. So what does the inverse binomial give to us? Well, it comes up with a warning sign as well. And again, that's typical with the binomial distribution. You've got to be careful with the values that come up. And it says x inverse is 379. So it suggests that 379 might actually be a critical value. But as before, I'm actually going to check that it is a critical value. So I'm going to work out the probability that x is less than or equal to 379. This should be fairly simple now on the calculator. We want binomial and the BCD, and the lower value is 0, the upper value is 379. And if I work that out, the probability that x is less than or equal to 379 is equal to 0.01225 ... which is equal to 1.2%, which is greater than 1%. So that tells us that 379 is not a critical value. So that means that anything that's 379 or above will not be small enough to be critical. And we know that 380 didn't result in a significant result. That was the calculation we did previously. So the calculator's given us an indication of the position of the critical region, but we do need to do a little bit of further work ourselves. So I'm going to do the probability that x is less than or equal to 378. So let's see what that gives us. Now that gives us a much smaller probability. It's 0.009244. So if I convert this to a percentage and round two significant figures, that's 0.92%, which is smaller than 1%. So 378 is critical, and anything lower than 378 will also be a critical value as well. So our critical region, or our critical values, are the set of values x, which are basically 0, 1, 2, ... all the way up to 378. So these values are all critical. Now, how would we run our hypothesis test in this situation? Well, our test statistic was 380. And 380 is not a critical value. So we can, at that point there, very clearly say the result is not significant. And then the conclusion follows on as it did previously. It's an alternative way of running the hypothesis test. But remember, it takes longer to find critical regions, so unless you're asked specifically to do this, it isn't advisable to do it because it will take up too much time, whereas the probability calculation to work out px is less than or equal to 380 took a few seconds, and then we could go straight to the conclusion from there. So this takes us on to example number 4. So eggs are packed in boxes of 6, which are then sold. During the process, some eggs are cracked. A sample of boxes is selected at random, and the number of cracked eggs in each box is recorded. So of course there are 6 eggs in a box, so there could be anywhere between 0 and all 6 eggs that are cracked. So part 1, calculate the mean number of cracked eggs per box. So this is where the graphical calculator comes into its own, because we do not want to be wasting time working out the mean here. Notice that it's only worth 1 mark as well. So this is where you simply want to input the numbers into your calculator in stats mode and get an answer for the mean. So here's what I'm going to do. I'm going to go into stats mode on the calculator, and then in list 1 I'm going to enter the number of cracked eggs, so 0, 1, 2, 3, 4, 5 and 6 in list 1, which is a vertical column. And then in list 2, I'm going to enter the number of boxes, so 163, 103, 28, 5001. So there's no real need to write this down as part of your working. I just wanted to make sure everyone was clear about how to do this. We then want to select F2, which is calc, and then we need to check that everything is as it should be. So F6 and set is our next choice. and we want to make sure that one var x list is set as list 1. So make sure that setting is correct, and you can use the F1 button to change to a different list, for example, if it's not set correctly. And then one var frequency, you need to make sure that that is set at list number 2. So use F2 to select a new list. If it's not correctly set up, it should be set up as list 2, because of course the frequencies are entered as list 2. You then need to exit from that menu and then select F1, which is one var. This then brings up all sorts of calculations, including x bar, which is the mean, which is 0.6. So part 2, it's believed that the number of cracked eggs per box may be modelled by a binomial distribution. State a modelling assumption that is necessary for a binomial distribution to be used to model the number of cracked eggs per box. So there are different conditions for the binomial distribution that we could address here. We already have the finite number of trials. Effectively, within a box, there are 6 possible eggs that constitute our trials. So we need to look at the other possibilities. Obviously, eggs can be cracked or not cracked, so there are 2 possible outcomes in each trial. But we also have the fact that each egg has the same or a constant probability of being cracked, and the probability of any egg being cracked is independent to any other egg being cracked. So, P is the probability that a particular egg is cracked, and we've got to use our answer to part 1 to find the value of P. Now, this relies on us knowing the mean of a binomial distribution, and we should know this. If x is binomially distributed with parameters n and p, the mean value for x is equal to n multiplied by p. So we know that np is equal to 0.6 because we know that from part 1, the average value x bar is equal to 0.6. We worked it out. So that means np is equal to 0.6. N, remember, represents the number of eggs in each box, which is 6. So 6p equals 0.6, and this then tells us that p is equal to 0.1. So part 4, calculate the expected frequencies of cracked eggs per box according to Rosa's model, giving your answers correct to 1 decimal place. So let's work out the probability of each of the numbers of cracked eggs. So how can I work out all of these probabilities very simply without having to do 7 calculations? So I'm going into run mode, which is mode number 1, and I'm going to choose the button that says option on the calculator, OPTN. So that's an actual button on the main body of the calculator, OPTN. After I've pressed that button, I need to choose the stat button, which is F5. And from there, we need to use the distribution button, or dist, which is F3. And from there, we can choose the binomial option, which is F5. Now, having selected that, I need to choose BPD, which is binomial probability distribution, which is F1. And then the calculator will come up with the words binomial PD and then an open bracket. Now, in the open bracket, I'm going to enter the value of n, which is 6, because there are up to 6 eggs in a box that could be cracked, and then the p-value, which is 0.1, and I need to separate them using the comma button as well. Close the bracket and then press execute, and then you'll see some numbers coming up in a curly bracket. Now, you can read the numbers in the curly bracket, but it's easier to actually see them in the format of a list. So if you use the upwards arrow on your little arrow tracker pad to just land gently on those curly brackets, you'll see they get highlighted in black. press execute again and a list of probabilities will come up on your calculator screen. You can use the arrows to scroll through them. So the first probability is the probability that there are 0 cracked eggs, which is this value. Then 1 cracked egg, which is this value. 2 cracked eggs, which is this value. Ignore the numbers down the side, 1, 2, 3, 4, they're a bit misleading. The probability will always start off with the probability of 0 happening and then go upwards from there. And then you can read off all of the probabilities, which obviously get smaller as the number of eggs gets larger. Until we get to the probability of 6 broken eggs, which is this. Now, how do we convert these probabilities into expected number of boxes containing this many cracked eggs? Well, if we go back to the total number of boxes here, we can work out the total number of boxes overall. So if we add together the number of boxes in this row here, we'll find that the total frequency is 300. So the sum of the frequencies is 300. So how do we convert these probabilities into expected frequencies? We need to multiply each of these by 300. So the expected number of boxes that contain 0 cracked eggs will be this number, 0.5314, but we multiply that by the total number of boxes overall, which is 300, and you can do that with all of these other values as well. And you will find you get values which are as follows: 159.4, 106.3, 29.5, 4.4, 0.4, and then 0.0, 0.0. I've rounded all my values to one decimal place. I know we're talking about expected number of boxes and there'll be a temptation to round to the nearest integer, but don't do that because it gives a misleading picture of what the expected values are like. Round to something sensible. Now, the last part of the question asks us to comment on whether Rosa's model is a good fit for the data. So let's compare the observed values with the expected values. So we actually predicted that there would be 159.4 boxes with 0 cracked eggs. There were in fact 163 in total with 0 cracked eggs, which isn't too bad a comparison. We predicted there would be 106.3 boxes with 1 cracked egg. There were actually 103. So we can go through the list comparing the expected number of boxes with the actual number of boxes, and the comparison isn't too bad. So because the theoretical frequencies, which we've just calculated, are quite close to the actual frequencies, the model can be described to be a reasonable fit for the data. Now we come to the final part of this question. So instead of selling eggs at the farm, Rose decides to sell them to a wholesaler. The eggs are now selected randomly and packed in open trays of 24. Rose believes that this will result in a change in the probability of an egg being cracked. She selects a tray at random and finds that 5 eggs are cracked. We need to conduct a hypothesis test to determine whether there is any evidence at the 5% level to suggest that the proportion of cracked eggs has changed. Read through this information again very carefully before you get started. So, the eggs are now selected randomly and packed in open trays of 24 eggs. Rose believes that this will result in a change in the probability of an egg being cracked, and she selects a tray at random and finds that 5 eggs are cracked. Again, in the question, we need to conduct a hypothesis test to determine whether there is evidence at the 5% level, and we are looking to see if the proportion of cracked eggs has changed. So, remember what x is. X is the number of cracked eggs. Now, the distribution of x has changed a little bit. It's still binomial, but the n value is 24 because the eggs are packed in trays of 24. the probability is still 0.1 under the null hypothesis. So H0 is P is 0.1. But H1, look at the information here and here in the question, we're testing to see if there is a change in the probability. So P is not equal to 0.1 is our alternative hypothesis. So this is clearly a two-tailed hypothesis test. Now, define P again. So P is the probability that an egg selected at random from the population is cracked. Now, where do we go from here? Well, we have a test statistic, which is that we know that 5 eggs are cracked. So we have to decide whether we're looking at the lower tail or the upper tail for this hypothesis test. Now, the way I like to do that is to compare the test statistic to the mean value. So the test statistic is equal to 5 because 5 eggs were cracked in the sample. Now the mean of x is NP, which is equal to 24 multiplied by 0.1, which is 2.4. Now, how do the two values compare? Well, 5 is obviously greater than 2.4, which tells us that we need to investigate the upper tail of the distribution. So it's a two-tailed test, but we need to focus on the upper tail when we do our probability calculation. If our test statistic had been lower than 2.4, the average value, that would tell us to look at the lower tail. So when we do our probability calculation, we simply have to do the probability that x is greater than or equal to 5 because we're focusing on the upper tail of this test. So we can set this up again in stats mode on the calculator. So remember how we've been doing this in the previous examples. We want to make sure we've got distribution F5, binomial F5, binomial cumulative distribution or BCD, which is F2. Data is always set at variable. Now this time the probability that x is greater than or equal to 5, well, you're effectively working out the probability that x is greater than or equal to 5 but less than or equal to 24. So your lower value is set at 5, your upper value is 24, and the number of trials is also 24. P stays at 0.1, and this gives you the probability, which is 0.08507. I'm going to convert that to a percentage and round it, so 8.5%. Now, how does that compare with the significance level? Well, the overall significance level of the test is 5%, but because it's a two-tailed test, we need to halve that for each tail, and so we're comparing this with 2.5%. So this is clearly greater than 2.5%, so this tells me that the result is not significant at the 5% level. We can still say 5% because overall the level of the test was 5%. Because the result is not significant, we do not have sufficient evidence to reject H0. And we do not have sufficient evidence to suggest that the probability of an egg being cracked has changed. Now, in our conclusion, we should never, for a two-tailed test, ever refer to an increase or a decrease. We should always refer to a change or a difference. So even if we get a significant result, we don't say that we've got evidence of an increase or a decrease for a two-tailed test, because that's not what we were testing for. We were testing for a change, so we need to reference that in our answer. Now, some people like to do two-tailed hypothesis tests using critical regions. Again, the process becomes more complex if you do this, but we can do this. So if k is a critical value, then the probability that x is less than or equal to k must be smaller than 0.025. 0.025 is, of course, half our overall significance level of 2.5%. Now, that's one possibility. The other possibility is that the probability that x is greater than or equal to k is less than 0.025 or 2.5%, because with a two-tailed test, we could have a critical region that's a lower critical region or a critical region that is an upper critical region. Now, how do you know whether you're looking at the lower critical region or the upper critical region? You decide by looking at the average value and your test statistic and comparing the two. So for our example, our test statistic was the number of actual cracked eggs, which was 5, and our average value, our mean value, which is of course NP, was equal to 2.4. So because 5 is greater than 2.4, that tells us we're looking at the upper tail. So we only really need to find this upper critical region here. Now, I will find both critical regions just as a matter of interest. We're going to use the inverse binomial calculation again to see what happens. So for the lower tail, for our lower critical region, I'm going to use binomial, inverse binomial again, and I'm going to set the area as being 0.025. And my number of trials has got to be the total number of eggs, which was 24. And my p-value, my probability value is 0.1. And that then returns an answer of x inverse equal to 0. Now, as before, we need to test out what this actually means. So I'm going to work out the probability that x equals 0, and I'm also going to work out the probability that x is less than or equal to 1, and we'll compare these with 0.025. So again, this can be done very simply on the calculator, and let's work out these probabilities. So the probability that x equals 0 works out to be 0.0797, which of course is 8.0%, which is greater than 2.5%. So that tells us 0 is not a critical value. And just as a point of interest, to show you what happens here, I'm going to work out the probability that x is equal to 1. And of course that's going to be larger, we know this, but I'll just work it out anyway. It's actually this value, which is 29.2%, which is very definitely larger than 2.5%. So actually, this shows us that the lower critical region is empty. There are no values in the lower critical region. So 0 is not a critical value, 1 is not a critical value, anything above 1 is obviously not going to be a critical value, so the lower critical region is actually empty. Now, how do we work out the upper critical region? So, again, using the inverse binomial on the calculator, I'm going to carefully set everything up. So the inverse binomial, now by the area, when the calculator looks for the area, it's looking for the area on the left-hand side. So we've actually got to input 0.975, because that would be the area to the left of the upper critical region. The area to the right of it would be the 0.025. Everything else is as before. The number of trials is 24 and the p probability value is 0.1. And let's see what the inverse binomial gives us. It tells us x inverse is equal to 6. So it's suggesting that 6 or above would be critical values. So again, we want to check whether this is actually correct. So to do that, we're going to calculate some probabilities. I'm going to calculate the probability that x is greater than or equal to 5, which we do already know from our previous question, and the probability that x is greater than or equal to 6, and we will see what these come to. So the probability that x is greater than or equal to 5 should be familiar. We worked it out previously. It is 0.0850 ... So that is 8.5%, which is bigger than 2.5%. So that tells us that 5 is not a critical value. Now, what about the probability that x is greater than or equal to 6? Well, that is equal to 0.0276 ... So that, if we work it out as a percentage, is 2.8%, which is also greater than 2.5%. So that tells us that 6 is not a critical value. So actually, I need to go one more and work out the probability that x is greater than or equal to 7. Now, the probability that x is greater than or equal to 7 is a smaller number. It's 0.00745, etc., or 0.7% to one decimal place, which is less than 2.5%. So 7 is a critical value. So our upper critical region is the set of values x, which are 7 or above. So 7 up to 24 would constitute critical values. Now again, for our hypothesis test, we look at our test statistic, which was 5. It does not fall into the critical region, so we don't have a significant result, and then the conclusion can follow from there as normal. It's a lot more work to find critical regions for a two-tailed test because you've got a lower critical region and an upper critical region. You can cut down the amount of work that needs to be done by doing this step here, which allows you to identify whether you're working with an upper critical region or a lower critical region. It can really save quite a lot of time, but ultimately you only really need to find critical regions if there is a particular reason for you to do that. You're asked to do it for example, or if you haven't carried out your experiment yet and you don't have a test statistic on which to base a probability calculation.